Hello, this is Benjamin Gordon, an MD PhD student at the University of Illinois at Chicago College of Medicine. This video is part of our Survivors Advising Scientists educational program, a bidirectional educational platform meant to connect our communities and increase scientific literacy and engagement. Our goal is to bring everyone to the table for scientific discussions related to cancer science and therapies. This is video module number 1, Scientific Hypotheses. In the upcoming slides and modules, we'll be discussing experimental design and experimentation, especially through a biomedical lens related to cancer research. In this lens, experiments are procedures in order to explain the causes of disease or discover new therapies. In order to do so, researchers need strong, well designed experiments. If experiments have inherent flaws, then patients might suffer from misinterpretation or misunderstanding of experimental results. Experimental results must be understandable, meaning clear, and reproducible, meaning that a scientist at one institution can perform an experiment, and a scientist at another institution, maybe somewhere across the world, can repeat the same experiment and get similar results. Experiments aim to extend knowledge beyond what is already known by forming a well informed hypothesis. Hypotheses will be covered on the next slide. Experiments aim to work on an unsolved problem. We could face unsolved problems in everyday life, and in biomedical research, there are many unsolved problems. Here are a few examples of both biomedical research unsolved problems and everyday unsolved problems. 1. There are currently not enough methods to detect cancer early. 2. There's currently a rash on my skin, and I don't know what it is. 3. I went to sleep with a full jar of cookies, but the jar was empty when I woke up. So, what is a research hypothesis, or plural, hypotheses? Hypotheses make an educated guess. Hypotheses are testable and falsifiable. Researchers need to be able to set up experiments to test a hypothesis. If you cannot prove your hypothesis wrong, it is not a hypothesis. For instance, if you hypothesize that unicorns fly higher and faster than bald eagles, this is not a great hypothesis because you can't get unicorns to test your experiment. Let's go over an everyday example. So, first we have background information, which is the known information. It's information already published by doctors and scientists. It is assumed to be true. For instance, I bought cookies from the grocery store last night. I put the cookies in my cookie jar. Now let's go over our unsolved problem. After my friends were over, there were no more cookies left. My friends are eating all my cookies. Now let's set out a goal. We want to figure out what's going on with our missing cookies. We have an objective here. I want to protect my cookies. Here is a research hypothesis. If I put my next batch of cookies in a locked drawer, then my cookies will not disappear like they do in the open drawer. Now let's take a look at that same research hypothesis. I'll repeat it. If I put my next batch of cookies in a locked drawer, then my cookies will not disappear like they do in the open drawer. This is a good research hypothesis because it is a well-informed prediction, is testable, and it's falsifiable. It's a well-informed prediction because it's an educated guess meant to advance our knowledge about cookie protection. Here, the hypothesis uses an if-then architecture. If I put my next batch of cookies in a locked drawer, then my cookies will not disappear like they do in the open drawer. Many, but not all, research hypotheses use this setup with the if-then. It's testable because one can compare the amount of cookies in the locked drawer versus the amount of cookies in the open drawer. So you can set an experiment up to test your research hypothesis. And finally, it is falsifiable. It's falsifiable because the hypothesis may or may not be true. Let's go over a biomedical hypothesis. So again, we have some background information here. The known information is 1 in 8 women will develop breast cancer in their lifetime. Early detection of breast cancer leads to more successful treatment than late detection of breast cancer. Now, this is information already published by doctors and scientists. Most people would assume this to be true already. Now we have an unsolved problem. There are currently a lot of women who develop late-stage cancer because it's not detected early. This is a problem that needs to be solved. Now let's set out a goal. Here's our objective. Researchers want to test a new imaging instrument, it's hypothetical, to detect breast cancer more accurately than traditional mammograms. Let's call it, for the purpose of discussion, super scanner. And there's the little picture of it to the right. Now, here's our hypothesis. If women undergo routine annual imaging starting at age 45 with the super scanner, then more cases of breast cancer will be detected earlier as compared to similar screening with traditional mammograms. Again, as in the previous example, the hypothesis follows an if women undergo routine annual imaging, and then statement, then more cases of breast cancer will be detected. Now let's take another look at this research hypothesis. If women undergo routine annual imaging starting at age 45 with the super scanner, then more cases of breast cancer will be detected earlier as compared to similar screening with traditional mammograms. It is a well-informed prediction because it makes an educated guess, an if-then statement here. It is testable because one can set up an experiment testing the super scanner against traditional detection strategies. And it is falsifiable because the hypothesis may or may not be true. It could be the super scanner, even though it's called the super scanner, may not work that well. Now, here is an exercise. Let's characterize the following choices about cancer immunotherapy as either known information, an unsolved problem, or a hypothesis. A, combining immunotherapy with traditional chemotherapy will shrink tumor size more than traditional chemotherapy on its own. B, many patients get immunotherapy and it's making national news. C, the Nobel Prize in 2012 was given to James Allison, a pioneer in immunotherapy. D, there's currently a need to understand why only few people actually benefit from immunotherapy. In the following slides, I will be going over the answers. So if you would like more time to independently think about this, please pause the screen before continuing. So B and C are background information. Many patients get immunotherapy and it's making national news. C, the Nobel Prize in 2012 was given to James Allison, a pioneer in immunotherapy. These are non-testable because they are already accepted as true. They are background information. D, there's currently a need to understand why only few people actually benefit from immunotherapy is our unsolved problem. This is a current problem that still needs to be addressed. And that leaves us with A as our research hypothesis. Combining immunotherapy with traditional chemotherapy will shrink tumor size more than traditional chemotherapy on its own. It's a well-informed prediction meant to advance our knowledge about a new type of therapy. Here, we do not have an if-then statement like we did in previous examples, but it still makes it a well-informed prediction, so it's a good hypothesis. It is testable because one can set up experiments or clinical trials to test combination therapy with traditional chemotherapy. And finally, it's falsifiable because combination therapy may or may not be beneficial compared to traditional chemotherapy. So, when you evaluate a research experiment design, whether you're at a poster session or talking to a doctor or a scientist, here are some initial questions to think about. These questions could be a great starting point to really organize your thoughts related to an experiment. So, what is already known about the disease? What is the goal for the research project? What is the hypothesis? Is the hypothesis testable and is it falsifiable? This is the end of this module. I'd like to take the time to thank Dr. Kidieski and the administrative staff of the University of Illinois Cancer Center for their support in this endeavor. Additionally, we'd like to give a special thank you to all the cancer patient advocates who provided feedback in the development of these modules. We'd also like to thank you for reviewing these modules, and we invite you to send any feedback on this module or suggestions for future content to sasep@uic.edu. Please feel free to move on to the next module on components of hypotheses. Thanks again.